Welcome back to the channel. Could our AIs be more human-like, at least in terms of energy efficiency, common sense, and fast incremental learning? In previous videos, I've shown how a person's knowledge is clearly organized in a graph of relationships with inherited attributes and exceptions. Further, I've shown that biological neurons are so slow that a graph cannot be a nebulous abstraction, but must be implemented in physical neurons. So I proposed a structure which can do this in cortical columns. With a graph, your brain can recall the attributes of anything it knows in a fraction of a second, including the web of inherited attributes and those pesky exceptions. In this video, I'm going at this from the opposite direction. Given some attributes, what is the most likely thing they represent? Your brain does this all the time. Your vision system is continuously identifying things in your visual field, and your hearing system is identifying words and meanings. At a higher level, your brain is looking for patterns and similarities in situations so you can decide what's best to do next. So given some attributes, how can your neurons find the thing they most likely represent? I thought this would be an easy problem given that neural networks do this very effectively. But like many problems in AI, it turns out to be a lot trickier, and the results surprised me. I'm Charles Simon, longtime AI researcher, software developer, and manager. Beyond AI, I've developed software for neurological test instruments and neural simulators. I created the Future AI Society to explore how neuroscience can inform smarter, more human-like AI. I'm using our open-source brain simulator project for simulations and demonstrations throughout this video series. If you want to experiment with the networks shown in this and other videos, you can download the Brain Simulator 2 from GitHub and try them out. You can also participate in the discussions on our Discord server at the link in the description below. At its core, the sensory half of your brain is about recognizing things by their attributes, something it does effortlessly all the time. You can recognize this A by its visual attributes, its 3 line segments. And if I tell you that Fido has floppy ears, that becomes one of his recognizable attributes too. It's reasonable to presume that the underlying mechanism for this sort of recognition is the same for all types of attributes at many different levels. Let's look at how this underlying attribute recognition system might work. We'll defer inheritance till the end of the video and start with a few individual neurons and see if we can make this work with synapses connecting them. We'll worry about how the synapse weights get set in a few moments. Consider this network where a number of attribute neurons are connected synaptically to 2 unique recognizer neurons. For demonstration purposes, I've put in 4 pattern neurons which can fire a pattern of attributes, like this. In the real world, these patterns would originate with real-world sensory input. We want each individual recognizer neuron to fire in response to a specific pattern of attributes. And we can see this in action by enabling recognition by firing the is attribute of neuron. And you can see that for pattern 1, recognizer 1 fires, and for pattern 2, recognizer 2 fires. Notice that it takes at least 3 spikes for each recognizer to fire. Couldn't we do it in a single spike? Well, yes, but what if there isn't a perfect match? We want the recognizer with the closest match to fire and not others. The only way to achieve this in neurons is to set the synapse weights so that the best match will fire first and poorer matches will take progressively longer to fire. That way, the best matched neuron will fire and can suppress the other recognizers with these negative synapses. So what are the desired synapse weights? We might initially think that because our pattern has 7 attributes firing that we want the synapse weights to be 1/7, so the correct pattern will fire immediately, and if there is a missing attribute, it will fire on the second set of spikes. The problem with this approach is that if there are 2 or 3 missing attributes, the recognizer will still fire on the second set of spikes. This means that if one recognizer has 1 missing attribute and the other has 3, there will be no way to prefer the better match. We can see that our criteria have morphed a bit. We are willing to trade off immediacy of recognition for better differentiation in the number of correct attributes. And this will work if we set the synapse weights to 0.05 and the recognizer leakage to 0.005. I came up with these numbers by experimentation. You can see that for a perfect match, it then takes 3 spikes to fire the recognizer. But if there is a single missing attribute, it will take 4 spikes, and another spike is required for each additional missing attribute. Now let's fire pattern 3. It's like pattern 1, but has 2 missing attributes. You can see that it takes a little longer for the recognizer 1 to fire, and when it does, these inhibitory synapses will prevent the non-winning recognizers from firing. It's a winner-take-all scenario. In pattern 4, we have attributes such that both recognizers have the same number of correct and missing or erroneous attributes, and then we have a tie, and both recognizers will fire at the same time. How long does this take in real time? A perfect match will take about 12 milliseconds to fire. And worst case, with only a single matching attribute of 7, the recognizer will fire in about 100 milliseconds. But the system can always give up the search at any time. Learning these patterns is a simple matter of setting the synapse weights. But Hebbian learning, or STDP, is not capable of accomplishing this, as I pointed out a few videos back, because it cannot set synapse weights with any degree of precision. So let's assume that each synapse has a maximum weight of 0.05, and the learning process simply sets the synapse either to its maximum weight or its negative maximum. Although I've set the learning parameter so this happens in a single spike, biological learning processes likely take many more. Now you can see that if I switch recognizer 1 to recognize pattern 2 and recognizer 2 to recognize pattern 1, now the system is reversed and it still works. Let's see this with an example as it fits into the neuron-based graph I explained a few videos ago. In this graph, I've set up nodes representing cats, dogs, and the attributes fur, tail, meows, and barks. Cats have the attributes of fur, tail, and meows, and dogs have the attributes of fur, tail, and barks. I've set up some shortcut neurons to help add the attributes. These just fire the relevant neurons to add the attributes into the graph. For example, this neuron labeled dog will fire the dog input and the has attribute relationship type and the 3 desired attributes, barks, fur, and tail. Notice that the system can accept as many attributes as we like in a single operation. After a delay, it inverts the relationship, and this is the relevant part for recognition. It adds the relationship that bark, fur, and tail are attributes of a dog. Here's where it sets the synapses needed to set up the recognizer for the dog column. Having done that, I can show that if I fire the dog input and the has attribute relationship, the 3 attributes will fire. Also, now I can fire the 3 relationships and the is attribute of relationship type, and the dog output will fire. I have a shortcut neuron which fires these. I can repeat this process with the cat neuron. I fire the cat input and its three attributes, meows, fur, and tail. And we can verify that things are working as desired by asking what has the attributes of meows, fur, and tail, and verify that it's a cat. And the attributes of barks, fur, and tail still works and verifies that it's a dog. But let's try some partial matches by searching for what has the attributes of barks and a tail. The dog output will fire, and it's difficult to tell in this demo, but it takes a little longer for this recognition to occur. So it's a slightly lower confidence result. What if we search for what has just fur and a tail? As we would expect, both dog and cat are found. So far, we've assumed every attribute is directly tied to each animal. But in reality, many attributes are inherited from higher level categories. For example, let's add my favorite fact that Fido is a dog, and then add the attributes that Fido is brown, small, and has floppy ears. If we search for brown or any set of hypothetical attributes which are unique to Fido, everything is fine. But what if we ask what has floppy ears, fur, and a tail? Now the cat and dog outputs will fire before the Fido output. So we need to make a few changes. First, recognize that our brains would always prefer to get the most precise answers, which are the things furthest down the hierarchy. So we'll need a mechanism so that if both dog and Fido fire, we'll know that it's Fido rather than the more generic dog that we're interested in. Second, we need to add an attribute so that recognizing a dog is a contributing attribute to the Fido recognizer. That way, if we see a dog along with just a few attributes of Fido, we'll once again know that it's Fido. Third, we need to remove some winner-take-all inhibitory synapses so that the firing of dog does not suppress the subsequent firing of Fido. Finally, we need to allow every search to spike a few more times after the first target fires to give descendants a chance to fire for a better match. I haven't implemented these features in this model, but I can see how they can be done. By starting with the single neuron case and carefully tuning the weights to distinguish small differences in matching attributes and adding competitive inhibition, we can build a spike pattern recognition system that is both biologically plausible and computationally efficient. I've shown some simple illustrations with a few attributes, but I leave it to you to imagine this working in the brain with millions of recognizable objects and possible attributes. This recognition process is going on in your brain all the time, even right now. Inheritance extends this further, letting us represent concepts more compactly, while still recognizing them accurately from their defining features. In the next video, I'll introduce the Brain Simulator 3, which is a conceptual step up, working on a graph of information rather than the individual neurons I've used in this video. If these ideas resonate with you, if you want to see where they lead, please like, subscribe, and hit the notification bell, because the YouTube algorithm won't surface videos like this unless you ask for them. And if you want to dig deeper, join the Future AI Society. It's free and help us shape the next generation of intelligent systems. And you can participate in our online conversations and our Discord server. And as always, thanks for watching.